that says determination of modulus K?
Yep.
Okay.
Yes.
So I want to take a minute or two and go over some of the techniques for measuring track modulus in the field. Like I said, for this class, I will give you the modulus. I will, and you sort of have a rough idea. Modulus soft, very soft tracks 3 to 10. Moderate track is sort of 15 to 25, 30. Stiff track is already 30 to 50 plus. Very stiff track, such a slab track, is 70, 80. But how do we measure it in the field? Because there are 3 different ways I'm going to show you real quickly. The first 2 just use straight measurement in the field. The third one involves a conversion using beam and elastic foundation theory that we talked about. So let's go through these very quickly. Okay, let me get my marker here. Here we go. Okay, so in all cases, when you do modulus in the field, you're really going to park. I mean, you could for the first 2 cases. For these 2 cases, you need to park a vehicle on the track. The vehicle has to be stationary because it takes a fair bit of time to get the information. For this case, you can use a vehicle moving along the track. Ideally, he should be moving slowly to minimize the dynamic effects, but a slow-moving vehicle works best. But you can even approximate this with a fast-moving vehicle. It just introduces a greater error because of the dynamics. But the first 2 curves, the first 2 methods, the deflection curve and the heavy light wheel load deflection curve, requires you to sit and park your vehicle on the track. Okay, so if you park the vehicle over the track, and basically what you want to do is you want to measure the change in each sleeper vertical displacement with and without the vehicle. So what you would do is, let's say in this particular case, I have roughly a 20 sleeper setup where I've gone in and I've used a surveyor's level to measure my initial position of each of my 20 sleepers. Actually, there are 19 sleepers in this picture. For some reason, it didn't go out to 10 here, but it doesn't make a difference. So I take the initial measurements without a vehicle. Then I bring the vehicle in. I park the vehicle right over here. And then I measure the deflection. Again, I take this at my surveyor's level and I measure my level for each of these 19 sleepers. I subtract those 2 values, and that gives me my vertical deflection on each sleeper. And you can see these points represent actual field tests. This was done at this is a 40,000 pound wheel load. This is a 50,000 pound wheel load. So these are 2 different wheel loads that were done here. But you can see you get the deflection. Once you get the deflection, you basically, what you want to do is you want to calculate the area under this curve, and then you basically calculate K is P over the area. So the area under the deflection curve is nothing more than the sleeper spacing times the sum of the deflection. So we had 19 sleepers. So this I goes from 1 to 19. So I basically take deflection 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 till 19. I add them up. multiplied by A, which is the sleeper spacing. That gives me the total area. And then I take PO, my load. Now it's obviously a static load because I'm parked on that spot. So V equals 0. So my dynamic load is equal to my static load. And so my modulus is K divided by the area. You see, it's a very easy technique, but it's time consuming. And you got to get a vehicle and you got to dedicate a vehicle to there. It also introduces a couple of errors, not the least of which is that very often the modulus deflection under load is nonlinear. And sometimes what happens also is you have this, sometimes there's a void in the ballast underneath the sleeper. So you come down and there's a gap there. So to overcome that, we use method number 2, which is the heavy light deflection load, which means I have to do 3 sets of measurements. I have to go back and I have to take my, I basically take my initial measurement with no vehicle on there. I come along with a light vehicle, such as a high rail vehicle or a motor car or something, and I measure my deflections for all 19 of the sleepers. And then I come back with my freight vehicle, and I measure the deflection under the heavy load. So I have my, again, using a surveyor's level, my initial level with nothing on there, and then under light load, and then under heavy load. And then I can then calculate my modulus as the heavy load minus the light load divided by the area between the deflection curves, which is really this area over here. And that's nothing more than the difference in deflection at each sleeper, again, 1 through 19 times A. Again, it's a very easy technique to use, but it requires a lot of dedicated time. The third technique, yes.
Don't you compensate the P, dynamic P, because of, when you are in static, but when you move on the wheel,
no, but,
then you're going to get the dynamic significantly.
No, because your deflections are static.
All right. Thank you.
Your deflections are also static because you're static.
Okay.
And that's a very good question because it leads me into the dynamic methods. So the third method is a dynamic method.
I understand. Thank you.
And the third method is actually probably the easiest one to do in the field, in the sense that it doesn't require you to park a vehicle there. It's just a little bit more difficult to measure the deflection under the wheel. You need to instrument. You need some instrumentation. So in this technique, I have my track. Some of these days I'm going to learn to draw straight on this thing. I have my track. I come along and I put some sort of instrumentation under this track to measure the deflection. It can be a deflectometer, it can be a LVDT, it can be nothing more than a spring-loaded maximum deflection measurement system. There are lots of techniques out there that are out there for instrumentation, but I measured, I basically set up the deflection under the sleeper, and I set it to 0. And then I let a train go by, or a car go by, or a locomotive go by. Like I said, preferably at low speed, but it can go at any speed. And I measure the deflection, the maximum deflection that I see at that sleeper. So whatever the maximum deflection is, I measure it. And so now I have a deflection. And I know the speed of my vehicle, so I know my dynamic load as well. Now I can use beam and elastic foundation equation to calculate K. So I can go back and I know my E and my I know what rail size I have. So I can go back and I can calculate beta, and I can basically, well, I can't calculate beta because K is unknown. So basically I can set up my equation W is equal to P beta over 2K. And since I'm dealing at the maximum point, I really don't need the rest of my deflection curve, because this is really W max is equal to P beta over 2K. And if I know W, I know P dynamic, because I know P static and I know V. I know EI. I can solve this equation for K. It's an iterative process. So it's a little bit of a pain in the neck, because because beta is the fourth root of KEI. So you can't. It's not an easy closed form solution to do. You would have to do it. You have to set up a spreadsheet and iterate it through. So if you're really lazy, Kerr in his book actually has it done, and has he done for a two axle bogey, so you can actually use this master chart to calculate the your K module, your K value. Now, unfortunately, he does this chart in English system, and I haven't bothered making it into a metric equivalent, so I'm sorry. But you can just as easily convert it yourself. So he has UIC 100 RE rail is like UIC 50, and 115 RE rail is like UIC 62. UIC 57, and 140 is UIC 70. And here he has the deflection divided by the load. So W divided by P. And then if you let's say your W over P becomes 0.015, you're using UIC 50 rail, your track modulus is about 2,000 pounds per inch, which is about, what's 2,000? 2,000 pounds per inch is probably around 3 or 4 megapascals. But you can do it directly from the equation. As a matter of fact, let's go back to the spreadsheet, and I'll show you quickly how you can do this from the equation from the spreadsheet. It's actually very simple. So I go back to my two-axle case. So let's say you have UIC 60 rail, just like I have over here. And let's say your wagon is a 90-ton wagon, and it happens to be going at, I want to go slow. So let's say we're going 20 kilometers per hour. There we go. So I went out there and I measured my track, and I found that I had 7 millimeters of deflection when I went past the 20 kilometers per hour. So what I can just do at this point in time is I can just change my modulus. So let's try 8, and I'm at 7.1. So let's try 8.1, still 7.1, 8.3, too much, 8.2. And if I wanted to be a little bit more accurately, I can work like this. So you see how you do it iteratively. So if I go out and I measure my deflection under a sleeper, and I know the speeds, and I know the axle load, and I know the rail information, I can get my modulus directly. I can get my K by just iterating back and forth. And that's how I would do it in the field. And it works. I've done this many, 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 many times in the field. So this is something that really and legitimately works. Just want to go back to my original problem. Okay. All right. That brings us into my next topic area, which is actually a continuation of this topic area, but I break it up because sometimes I take too long to go through a class. Oops, what happened here?
Alan, can I ask a question regarding the last slide that you showed?
Which, okay,
the calculation, when you said that...
what I did on the spreadsheet? What I did in the spreadsheet,
Yes.
or what I did in the slide? Okay.
No, in the spreadsheet. But you take only 7 millimeters when you pass in 20 kilometers per hour. It also takes into account the other wheels.
Yes,
not a
in this
single
case
wheel.
it does. In this case, it
Okay.
already did. You see, because
Okay.
I was using the
Yes, in
the
total.
double wheel case.
Yes, okay. Mhm.
So
Right.
all you need to do at this point in time is you have to measure your deflection.
You need to have all the information, okay, regarding the slippers, their distance, and the type
Well,
of...
you don't really need the sleeper distance because it really doesn't enter into this calculation. You need the axle spacing, you need the rail information. Yeah, you should be, and you need the speed, and you need the weight of the vehicle.
Okay, thank you. Mhm.
So if you're out in the field, if you're doing the biggest problem here with this method is that you have to do some instrumentation. You have to have some way to measure the deflection as you go by. The other techniques, which were stationary, you can get away with a surveyor's level and without any instrumentation. So this is, and that, what I've also seen people do, if you want something really simple to do, is I've seen them glue a ruler or a scale vertically to the sleeper, and then use a surveyor's level and from a distance and watch and just keep an eye on the scale. And as it deflects, you figure you look at measure the maximum one and take it off. However, you measure the maximum deflection. Any other questions? There is my other presentation. No, did I lose my other presentation? Hold on a second, bear with me for a minute. Let me see what happened to my other presentation here. I must have closed it. That's what happened by accident. So let's find it here. There it is. Now the problem here is I can't use my scale. So let me see if I can do this now. I have it. Okay, good. We're back in business. Okay, so we're going to talk about distribution of a load in the track. And so again, very important to remember that the purpose of a key purpose of the track structure is to distribute the load in the track. So we talked about this very briefly before, that basically what we're looking at, we just went through an exercise where we just calculated some of the deflections and moments in the rail, but we still have to go about what happens to the sleeper, which is also called a cross tie, to the ballast, to the subballast, to the subgrade. Now, let's put things in perspective. The railroad track, when you take a step back and look at what it really does a phenomenal job in terms of distributing the load in the track. So if I come back to the wheel rail interface, the stresses in my wheel rail interface are of the order of 700 megapascals. And we're going to spend a lot of time talking about that next week and the week after. And we're going to spend, we're going to get into a little bit into wheel rail contact stress. The bending stresses, which are directly associated with the moments we just calculated, and we're going to calculate the bending stresses here shortly as well, are of the order of about 200 megapascals. Then we said that what happens is that, remember, the rail, the wheel, the rail then takes that force and distributes it over anywhere between 5 and 9 sleepers. In fact, we went through the exercise of showing that this middle sleeper carries between 20 and 40% of the load only. So the stresses at the top of the sleeper are now of the order of about 1 to 2 megapascals. I've taken my wheel rail contact stress environment of 700 megapascals and I brought it down to about 1 to 2 megapascals. Then the track, furthermore, takes the load and distributes the load from the sleeper. Well, next one is the bottom of the sleeper. Sorry, next one is the bottom of the sleeper, and this is the load that goes through the ballast. So the load that's distributed to the top of the ballast is of the order of 0.5 megapascal. And then that load, in turn, is distributed down into the subgrade, the soil, whatever's down there, be it the original soil, or if it's a fill material or whatever is down there. And this is usually very, very weak and very, very soft. So we got to we have to reduce stresses to the order of 0.1 to 0.1 to 0.2 megapascals. So look what just happened. We've taken a stress at the wheel rail interface of the order of close to 1,000 megapascals, and we've reduced it to about 1/10 of a megapascal, which is a factor of what? 10,000? So one of the primary purposes of the track structure is to take that load and keep reducing it so that at the rail sleeper interface, it's within the strength of the sleeper and fastener system and elastomers that are over there. At the sleeper ballast interface, it's at the strength of the ballast. At the ballast subballast interface, it's the strength of the subballast. At the subballast subgrade interface, it's at the strength of the soil or subgrade. And as you can see, the numbers are very dramatic. Okay, I'm going to a lot of time. I'm going to save the review of beam elastic foundation theory for a little bit later because we've already done this. I'm going to assume that you know how to do this for calculating the deflections and moments. We just went through this exercise, and so I'm going to stop. I'm going to skip through that, and I'm going to be prepared next week to come back and answer any questions on this one, because I suspect you're going to have questions. But now I want to talk about stresses. Okay, we've used the beam and elastic foundation model. We just showed you this is the single wheel case. This is the spreadsheet I showed you. And we see that there's a maximum moment here of 55 million Newton millimeters, and a maximum reverse moment here of the order of about minus 10 million Newton millimeters. And I want to convert this into a stress because I want to know what's going on into my rail. So I have my rail here. I have my wheel here. I have my rail cross section. Oops. I'm not gonna make my living as an artist, I'll tell you that. So how do we calculate our stresses? Okay. So hopefully you all remember the equation MC over I. So we have, again, going back here, we have two maximum stresses, right? We have a maximum bending moment positive stress, and we have a maximum bending moment negative stress. The maximum bending moment positive stress is such. Let me draw this a little bit better. Okay. So underneath the wheel, it's positive. How do we know it's positive? Remember the deflection curve? The deflection curve is down, right? We're going to deflect under the wheel. So at this point, right, I have a moment here and a moment like that, right? Hopefully all you remember that from your mechanics. So when rail sleep positive means I'm in tension in the base and compression in the head. When I have my uplift zone, my moment is flipped, it's reversed. And so in my reverse moment zone, in my zone where the moment has gone negative, I'm tension in the head and I'm negative in the base. So I've reversed. So how do I calculate this? Well, I calculate it using my friend MC over I. So underneath the wheel, my positive moment, MC is defined to be the distance between the neutral axis and the location I'm measuring. So if I'm measuring the tension in the base of the rail, C is the distance between the neutral axle and the base of the rail. And as we saw a few minutes ago, it's tabulated. Just look it up. I is look it up. So this stress right over here is nothing more than M0, the maximum stress at point X equals 0, times C over I for a single wheel. If we have two wheels, then you have to get the maximum moment under two wheels. So you have to go back to the spreadsheet and get the maximum moment under two wheels. So that's the stress at the base. The stress at the railhead this distance here is H minus C, right? H is the height of the rail. C is the distance from the base to the neutral axis. So the distance from the neutral axis to the head is H minus C. So my stress in my head is now M0, again for a single wheel, H minus C over I, and it's compression. Everybody understand that? Are we clear?
Yes.
Yes.
Okay, we'll do some examples in a couple of moments, but first I want to make sure we understand what happens in the other zone. So let's erase all my ink. So if I'm in the uplift zone, my moment now is negative. C is still the distance between the neutral axis and the base. H minus C is still the distance between the head and the neutral axis. But now I have tension in the head and compression in the base. So my stress at the rail base is MC over I, but M is the moment over here at distance X. And my stress in my head is M H minus C over I, where M again is the moment, same moment over here. This is M of X. But this is now to go to the head, I have to go to, I use the H minus C. So let's do an example. Okay, so let's do a simple example. I have a 22.5 ton axle load vehicle. So I have my same 90-ton vehicle on 4 axles, 8 wheels. And it's operating at 80 kilometers per hour. The same one we had as the problem before. Okay. My modulus is 6.9 megapascals. I have UIC 60 rail. This is the same problem we did in the spreadsheet before. Let's do the single wheel case to start with, just to make life easy, because I want you to understand the concept. So we do the single wheel case. The maximum moment will occur at X equals 0. So we know the moment at X equals 0 is equal to P dynamic over 4 beta. And beta is the 4th root of K over 4 EI. So if you remember from the spreadsheet, my moment, just to make it easy to pronounce, is 55.6 kilonewton meters, or 55 million Newton millimeters. It was UIC 60 rail, so I was 3055. I needed that for the beta, right? C, the distance, again, C is the distance from the neutral axis to the base, 81 millimeters. H minus C is the distance from the head to the neutral axis. So it's 172 minus 81. So what is that? 91 millimeters. So that's 91 millimeters. So the stress at the rail base is M sub 0, 55.6 kilonewton meters, times C, which is 81 millimeters, divided by I, which is 3055 centimeters. So we got to make sure your units are consistent. So you got to convert this to millimeters. And that gives me a stress of about 147 megapascals at the rail base in tension. My stress in my rail head is the same moment, 55.6 kilonewton. Again, to be consistent, I really should be using this number, right? Because this number allows me to be consistent in millimeters. I want to really be all my dimensions in millimeters. I never want to cross dimensions inside an equation. It's going to go. It's a recipe for disaster. So 55 million Newton millimeters times H minus C, which is 91 millimeters, divided by I, which is really 305, 300, what is it? This is 3055 times 10 to the fourth, right? So what does that give me? 30 million. If I did it quickly in my head, 30 million millimeters. And then my stress in my railhead is minus 1.66 megapascals in compression. Everybody understand how I did that?
Yeah.
Okay, bending stress we've already went over. Okay, so again, if you're dealing with an axle as opposed to a single wheel, you have to use the moment, the maximum moment at in the area of the axle, and then you have to use the maximum uplift moment, which you have to get from beam and elastic foundation theory. But if you're just looking for the maximum single stress under a wheel, this is going to give you that number without having to go through all the other numbers. And if I would, again, if I plot my stress curve, it looks amazingly like my moment curve, which it should be, because this is just MC over I. Okay, I'm just going to quickly review tie loading, and then I'm going to get into some of the other loading mechanisms. Okay, so to calculate the load on the sleeper,
אני שמעתי, אבל עכשיו...
hopefully that wasn't a question for me. Okay, so I calculate my maximum tie loading for a single wheel will be underneath the wheel. So I know W0 here is equal to P beta over 2K. And the force on this sleeper, if my tie spacing is A, sorry about that. My tie spacing in A, then my force is KW0A, where K is my modulus, W is P beta over 2K, and A is my tie spacing. So it's P beta A over 2. And we did some calculations on that. I'm not going to go over again. Okay, so at this point in time, I know how to calculate the force on each of my sleepers, right? This is KWA as a function of the deflection. This is the force on sleeper 0. This is the force on sleeper 1. So this is what, 34 kilonewtons, 30 kilonewtons, 20.6 kilonewtons, 11.6 kilonewtons, etc. for this particular case. The next thing we want, so if we want to calculate the bearing stress on the tie surface, on the sleeper surface, it all depends what your configuration is. If you're on wood tie track, wood sleeper track with conventional tie plates, then a tie plate, looking at it from the bottom, has an area A of the tie plate. And so the stress on the top of a sleeper, of a wooden sleeper, is nothing more than the force one force, so this 35 kilonewton, divided by the area of a tie plate. And that stress has to be somewhere below, depending on the type of sleeper, has to be below about 3,000 kilopascals. If you're dealing in the concrete tie world, the same ground. Oh, it's 2 copies. If you're dealing in the concrete tie world, then the bearing stress on top of your concrete sleeper is nothing more than the area of your tie pad, or the area of the base of the rail. So instead of a tie plate, you calculate the area of your tie pad. And the stress, again, is the force, which we calculated back here from KWA, over the area of the tie plate pad. So let's do a problem. Let's say we have a vehicle such that the dynamic wheel load is about 50 kips. So we're talking about about 224 kilonewtons. You got to forgive me. I sometimes slip back into the English system. The dynamic wheel load would be, again, the static wheel load times the speed, using the ARIMA formula. So if the dynamic wheel load is 224 kilonewtons and the center tie carries about 25% of the load, then the force of the tie is about 56 kilonewtons. Not out of line from what, a little bit higher than this particular case, because we're dealing with a more heavier dynamic load. Okay. If the area of this is a little bit bigger. This is a tie pad. So if I had a typical pad, if I had a typical concrete pad, the area would be probably closer to the order of about 30,000 square millimeters. And my stress would be 56 kilonewtons divided by 30,000 square millimeters. And that would be of the order of about 0.35. Is that right? No, 30 into 56. So that's about the order of, so it'll be of the order of about 0.2 megapascals, which should be significantly lower than the bearing stress of the concrete. So I really shouldn't be having a problem. But if I was dealing with wood sleepers, this actually could be a problem. And we run into this problem more with wood sleepers, but this is a quick way to check the bearing stress on the tie surface. What's more relevant for you and for the concrete tie world is what's the stress at the bottom of the tie. Now, this is particularly important because ballast is not that strong. A good ballast may have a strength of about 600 kilopascals. A poor ballast, and I consider limestone, by the way, a poor ballast. I know it's commonly used in Israel. I consider limestone as a poor ballast. I like things like granite. So a limestone may be only good for about 300 to 400 kilopascals. So I have to make sure the stress on the bottom of my sleeper is less than about the strength of my ballast, which, if again, good ballast 600 kilopascals, poor ballast 300 kilopascals. Now, in this case, as somebody asked earlier on, I need both wheels. Because now I have 2P. Now, you'd think that the stress is nothing more than 2P over A, where A is the bottom of the tie, right? Well, if you think that, you're wrong. And the reason you're wrong is that we tamp sleepers. And the reason we tamp sleepers is we want the sleeper to be supported underneath the rail seat, where I have my wheel loads coming down. So ideally, I have this situation. What I never want to have is a situation where my ballast drifts and I'm supported over here and I have a load over here. Anybody want to tell me why I don't want this situation? Come on, what's going to happen if my ballast is supported underneath the tie, under the center of the tie? Somebody take a guess.
Will break the concrete.
Absolutely. Absolutely. You're going to fracture the concrete. If it was wood, you'd fracture the wood. So all railroads anywhere in the world, even in Israel, do not want to have a lot of support under the center of the tie of the sleeper because they don't want this to happen. They want their support primarily here. So the bearing area of a sleeper is usually approximated as 2/3 the length times the width, where L is the length of my sleeper and B is the width of my sleeper. So coming back here, the stress on my ballast, the stress on the top of my ballast layer is 2 times my dynamic tie force. Again, this is the tie force. This is my friend over here, 35 kilonewtons, divided by 2/3 the area, which is 2 times the width times the length, 2/3 the width times the length. So let's do a problem. Okay. Let's say I'm running a train very fast and it has a high, and I have a heavy locomotive in the front of it. And it's generating a dynamic wheel load of about 311 kilonewtons. And it's very stiff track. It's a slab track. So that I go through my calculations, I find that center tie is carrying about 40% of the load. So all of a sudden, that center tie under this type of loading is carrying 125 kilonewtons, which is a pretty good load for the tie. So I have 125 here, and I have 125 here. Then I have a concrete sleeper that's 2.7 meters long and 300 millimeters wide. So I calculate the area as 2/3 times 300 times 2,600. And that gives me 520,000 square millimeter bearing area on the bottom of the tie. So this is 520,000. So my stress is 2 times 125 divided by 525,000 is 0.58 about 0.5 megapascals. If I had a really good ballast, I'm okay. If I had a really poor ballast, I'm not okay. So if you're the designer of this track, you need to make sure you specify a ballast that will support 400 0.48 megapascals or 480 or 480 kilopascals. And this is where design comes in, because now if you're a designer, you have a choice. Do I go for the very expensive granite, which I don't even need, or do I go for the much cheaper limestone? Well, if my dynamic load was 150 kilonewtons, let's make it 155 just to make life easy for me, then my stress would be 0.24 megapascals, and I can get away with the cheaper ballast. So all of a sudden, I'm specifying my ballast based on what my stresses are underneath the sleeper, because if my stresses are going to be above the strength of the ballast, then guess what's going to happen? The ballast is going to abrade, it's going to generate fines, it'll foul up, it'll mud spot, it'll deteriorate very quickly, and then you'll have a real problem right there. So this is a more typical type of situation. Let's say I have a more typical Israeli type of load environment where I have 222 kilonewton dynamic load, and it's a soft track, so it's the center tie is only carrying about 25% of the load. So the load of my tie is 55.6 kilonewtons. I have in this case, just to make difference, I have a slightly different concrete sleeper. I have a smaller concrete sleeper. So I say a metro sleeper. Metro concrete sleepers are generally smaller than the railroad concrete sleepers. Not all concrete sleepers are the same size. As a matter of fact, concrete sleepers come in all sorts of sizes. So this particular size that I picked has about 420,000 square millimeters. So the stress is 2 times 55.6 kilonewtons divided by 417,000 square millimeters. And that gives me a stress of about 266 kilopascals, which is less than even which is within the range of my cheaper ballast. So I can get away with my cheaper ballast as well here. And, there's other examples you can go through. I just want to very quickly show you what happens with a center bound tie. Sorry, I'm using a wood tie example instead of a concrete tie example. I'll have to change it sometime for a concrete tie example. Okay, so a center bound tie in the worst condition, I have F here, F here. So it's subject to 3-point bending. Anybody want to tell me what this distance is? Come on, what's this distance? Come on, people. I got a railroad track.
750 millimeters.
Yep, it's a little bit more than the gauge, right? Because we're looking center to center. So it's the gauge plus the width of the railhead, right? Mm-hmm. Half width railhead here, half width railhead here. Divided by, so this distance is half of that. So this distance is the gauge plus the width of the railhead. And this distance is half of that, so it's about 756 millimeters, to be a little bit more exact. You said 750, good estimate. You picked a smaller railhead than I picked. And then the stress is nothing more than MC over I for a rectangular section, right? So let's take an example. (222 kilonewtons). Oh, sorry. 56 kilonewtons. The moment is 756 millimeters times 56 kilonewtons, or about 442,000 kilonewton millimeters. The stress so the moment here is 42,336. The stress is MC over I, right? This is a rectangular cross section of the, so this is B, this is H, C is H over 2. So C is H over 2. And hopefully you all remember that for a rectangular cross section, the moment of inertia is BH cubed over 12. If not, you're going to have to go look it up in a manual somewhere, because I'm going to assume you know how to figure out how to do moment of inertia somewhere. But if I go through and I just do my calculations for my stress now, moment 42,000 kilonewton millimeters, C is the height over 2. B is BH cubed over 12. Then my stress becomes 35 megapascals. The bending stress of most of the strongest woods is of the order of about 10 to 20 megapascals. So you can see that the stress here is double the stress of this particular wood tie. In concrete, it will all depend on the strength of your concrete. But remember, this is in tension. So depending how much pre-stress you have in the concrete at the very top, there's a really good chance you're going to crack the tie right over there. And then it's going to fracture. Okay, I'm gonna wait for the analysis of the ballast of subgrade till next week. Anybody have any questions for me now on what we've covered so far? So what I want you all to work on that problem that we talked about for beam and elastic foundation, using both tabs of the homework problem or the work problem. One tab is a single wheel. The second tab is an axle or 2 wheels. And again, if anybody, I think you're going to not have any problem. You're going to go through these notes, you're going to go through it, you're going to look at the spreadsheet. It's going to be very obvious once you start working out how it works through. Just remember to keep track of your signs, keep track of your units. Make sure you use an absolute value if you're going to use a second axle, so that you don't have any negative numbers underneath your signs or exponents. Remember, it's an e to the minus beta x. If you have a negative value for x, that's going to become e to the plus beta x. It's going to blow up big time. You're going to get some really ridiculous numbers. And we'll continue next week. Hopefully, we'll finish up stresses, and we'll start getting into the world of the rail, which is one of my favorite areas. Nothing else. I personally wrote a book on rail maintenance grinding, so an area that I have a lot of fun with. Sort of out of time. If anybody has any pressing questions, I'll be glad to answer them. Other than that, We'll see you next week, and hopefully I'll try to get my video work. I have no idea what happened with Zoom today. Zoom sometimes gets very, very finicky. If it's really giving me a problem, I'll switch to my laptop, and this is my desktop, which I prefer because it's a bigger screen. See one chat.
Thank you.
Thank you.
Hey, somebody asked me a question. Is K representing the stiffness combination of the sleepers and the soil? Yes, it's the stiffness combinations of the sleeper, the ballast, and the soil, all three. Okay, we'll see you all next week. Take care. Have fun with the project. I know you'll all enjoy it.
Thank you. Thank you.
Thank you.